Let's take a look at one of the Chapter 9 problems. Again, not one on the end of chapter list, but one that has, lots of relevance for a bunch of them that are on the end of chapter list, and also for some of the mastering chemistry problems from Chapter 9. The one I've decided to take a look at is problem 9.88 in the Brown and LeMay textbook. It's one of these that asks you to determine the structure of a molecule and then think about any distortions from the ideal geometry that the molecule may have. And the one they want us to take a look at is phosphorus with a chlorine and 4 fluorines. And so right off the bat, I want you to, from the Chapter 8 type material, we have a third row central atom, and then lots of electronegative ones, including fluorine, with looks like 5 outer atoms. We're likely set up for a molecule that's going to have more than the standard octet, and this one is indeed going to be one of these. Now, the questions are, determine the geometry of the molecule, what they call the electron domain geometry, and then eventually the molecular geometry, and talk about any deviations from this. So remember, in Chapter 9, before you can do anything about talking about geometries, you have to draw the Lewis structure of the thing. At least get the basic mapping and then refine it into the more, more refined structures after that. So drawing a Lewis structure of this thing, pretty standard. Phosphorus in the center. We have 5 outer atoms, and so I'm going to arrange them, around as symmetrically as possible. And this one, put a chlorine, fluorine, and then the 4th fluorine here. There's all 5 of them, and sort of this pentagonal arrangement. We count up the total number of valence electrons in this thing. We have a phosphorus, column 5 of the periodic table. Chlorine sits in column 7 of the periodic table. Fluorine sits in column 7 of the periodic table. There are 4 of these. We have 40 electrons to put into this thing. So it's going to be a pretty good size structure. So away we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We put a pair of electrons between each. I have 30 to go. Now I turn my attention to the outer atoms, and as usual, they need 8, have 2. Need to add 6 more, got plenty to go. So away we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Oh my gosh, there they all are. We have used up all of our valence electrons. All the outer atoms are happy. Now, of course, we have to turn our attention to the central atom. I have no more electrons to give it. It certainly doesn't need any. It has 5 bonds on it. It has more than the normal valence electrons. It has 10, but that's okay. This is the type of molecule where this would occur. So here's the general mapping of where the electrons are located. And as we've talked about plenty of times, this is the beginning of your Lewis structure, or beginning of your geometry based on the Lewis structure. But now we have to decide what is the class and, what is the geometry of this thing. With 5 sets of electrons around that central atom, we're in the trigonal bipyramid family here. And so so I'm going to go ahead and trigonal bipyramid. All right. And so there is the answer for part A. Draw the Lewis structure and decide the electron domain geometry. We're in the trigonal bipyramid family. In fact, this will be trigonal bipyramid geometry as well, simply because there are no lone pairs anywhere on the central atom. So this is going to be a trigonal bipyramidal structure. Now, part B on this particular problem simply asks you to speculate which was going to demand more room, the phosphorus-chlorine bond or one of the phosphorus-fluorine bonds in this molecule. And this one's relatively straightforward as well. If you look at the positions of these things on the periodic table, fluorine sits right above chlorine on the periodic table. They're both members of column 7, as we've already noted here. Chlorine is larger than fluorine. It's a larger atom since it sits in row 3 rather than row 2 of the periodic table. And so of the 2 types of bonds in this molecule, I would be pretty confident in saying the phosphorus-chlorine bond will require more space than the phosphorus fluorine bond will. So what we have to decide then is, where does the chlorine go in the trigonal bipyramid structure? And remember, in the trigonal bipyramid, the roomiest location of the two parts of the trigonal bipyramid is actually in the equatorial or triangular section. So remind you of that and of the better geometry drawing of these things. The trigonal bipyramid. So here's a good way of drawing the trigonal bipyramid before I fill in any of the outer atoms. Remember, we have this linear axial region, it's called, and we have this triangular equatorial region. And of the two, the roomiest one, the one that has the fewest number of 90-degree interactions, is the equatorial region. So my large one is going to go there. That's where the chlorine is going to be. The other four positions are going to be where the fluorines are sitting. And I'll draw them in like that. And there is sort of an idealized trigonal bipyramid with the chlorine positioned in its, in the equatorial region of this particular geometry. So there's a nice representation of the molecule with its geometry taken into account. It will have trigonal bipyramidal molecular geometry as well. And then finally, part D asks us to think about, okay, now that you've drawn your trigonal bipyramid, will it have any distortions from the idealized 90-degree and 120-degree bond angles? And for this one, yeah, it probably will, because not all the bonds are identical. Some of these atoms are larger than others. The chlorines on the outside, again, the one chlorine is larger than the fluorines. And so if I had to draw it in a kind of a distorted manner, that big chlorine out here is going to have the effect of pushing the fluorines in the axial area back just a little bit. I may be exaggerating it here for effect, but it's going to make the bond angle slightly larger than the classic 90 degrees. Call it 92, 93 degrees. It will probably also have the effect of shrinking down the bond angle between the two fluorines in the equatorial to something less than 120 degrees, and the bond angle between the chlorine and the fluorines here in the equatorial zone slightly greater than 120 degrees. So yes, this thing will be distorted, and everything will be kind of pushed away from the larger outer atom, the chlorine, in this molecule. So there is the Lewis structure, the geometry of this thing, consideration of the space, a chapter 7 topic. Chlorine is a larger atom than fluorine. The idealized drawing of the geometry. And then here, the final answer for part D, the slightly distorted version of the trigonal bipyramid. Distorted because the chlorine is a little bit larger than the others, and it's going to kind of push everything a little bit farther away. So there is problem 88 out of the text. A relatively straightforward one with a lot of, basic geometry type things wrapped up in it. So keep that in mind, look it over, build a molecular model of this if you need to be able to see it a little more clearly. It's a very helpful thing to do. Really get your mind centered on the three-dimensional nature of these things, and go forth and think geometrically for a while. See you later.